Good morning, everyone. My name is Tesfalem Welearegay. I'm from Uppsala University. My presentation will be Pristine, gold, and copper decorated nanoporous nickel oxide films for selective CO and NO2 gas sensing. So I will have my introduction and fabrication and deposition of metal nanoparticles and oxides and surface physical status of nickel oxide. And we will see also nickel oxide gas sensing properties for CO and NO2. And finally, my conclusion. So as we may see that from the previous lectures, we have seen that the metal oxides can be used in many applications in our day-to-day lives. So we have in the industrial processes, environmental pollution controls, indoor air quality, as well as in the body functions that have the easily growing, let's say, fields in disease diagnosis through oxides, electron noise. So in all cases, what we see here is the most important with the sensitive layers and also with the heating powers of the systems. So we will not see more of this application in this with these active materials and modifying with the power consumption. So what we want to see here in our presentation is I will see how these active materials can be either not only with the mass productions and also not only when the active materials surface properties, it's also with the power consumption that have now a very successful metal oxide to be used. So when we are dealing with fabrication of metal oxides for sensor materials, mostly we use chemical vapor depositions or other chemical synthesis developments, as well as also physical vapor deposition methods. But in our case, that we have now this advanced gas deposition technique, which allows us to fabricate now a sensor arrays of different thicknesses, different porosities, as well as also with different levels of purities. So it's a very simple system that we are producing this metal nanoparticles or metal oxides from their precursors of pure metals. For example, if you want to metal nanoparticles, we use the precursor of the metal itself. And when we use a metal oxides, we mostly use the metal precursors and with an oxide. The system is very simple that you have a metal precursor, a different vapor chambers, so that the system is the metal precursor is heated to a given temperature, and therefore it is transferred to the upper chamber. So you can place different type of substrate over here, and you can also make a multi-sensor systems from the one deposition difference. So we could produce metal nanoparticles, pure metal nanoparticles from pure metal, let's say, element. And we can also produce highly porous metal oxide. The very important thing here is we can have the nickel precursor and combine an oxide. So there is an helium gas or a carrier ones, and there is also an oxide supply. So you have a vapor melt that is, let's say, oxidizing with the oxide, with the oxygen, so that you have pure metal oxides deposited on the substrates. So you can have as many as you want, the number of substrates, so that you are not, let's say, guided by a silicon or something alumina or something glass ones. So you will have now a different substrate on these substrates, on the substrate holder. So you can manipulate this the thickness of the metal oxide films, or you can also have, let's say, a porous materials of these ones. So by controlling the pressure, the induction power, inert gas, heat flow of oxygen gas, and the speed of the substrate heaters. So we have now previously produced different type of nanoparticles, depending on the speed parameters, and also depending on the powers. You could have very monodispersed nanoparticles. You could have also very continuous one, or a thick film of, let's say, layers of nanoparticles, very continuous ones. At the same time, you can also have a nickel oxide, a very porous one, nickel oxide films, copper oxide films. So you can control the thickness, at the same time, the porosity, as well as the polycrystallinity, which is very important in the gas sensing. So as deposed film is highly porous and polycrystalline films of different thickness, we can have the surface of the nanoparticle can be tuned based on the deposition parameters. So the idea is to produce a very porous porous metal oxides and polycrystalline, so that we would have now a very high absorption of molecules. So when we use the nickel oxide fabrication surface characterizations, we see also very thick and thin layers of nickel oxides and very porous. So they're very highly, let's say, densely populated with nickel oxide grains. So when we see now the deposition temperatures, I mean the annealing temperatures, we see now a big change at 400. There is a very change in the grain size of the nanoparticles that is grown. And depending on the thickness of the molecules, the thickness of the nickel oxide, we will see also different proportions of the grain size upon, let's say, annealing at different temperatures. And we've seen also, we have for the power that at the lower porous nickel oxide here, we see also a smaller grain increase because of the, let's say, you have a thin layers. And you have also nickel oxide with high power of production, and we have, let's say, greater grain size. Depending on this grain size or the particle size, we will have now different absorption size for the molecule we want to determine. So this is the cross-sectional image of this one, nickel oxide. So we in all the films we have a sharp diffraction peaks, which is very polycrystalline, changes with annealing temperatures, and the annealed nickel oxide film show now a rapid growth at 400 degrees centigrade now. This is the point where there is a change in the crystallized size of the nickel oxide. So having this nickel oxide thin films, we want also the electronic and optical cells of the nickel oxide. So as you can see, there is now nickel oxide 3 different depositions, different thicknesses with 0.5 micrometers and 0.1 micrometers. So we see also, depending on the thickness of the nickel oxide, we see a difference band gap energies. As we calculate from the tau plot, we see the ones with nickel oxide, the thinner ones have now almost 3.94, almost 4 band gap energies. Whereas with the thickness of now almost 1 micrometer of nickel oxide, we see 3.87. So nearly by just developing a thinner or thicker of nickel oxides, we are just manipulating or calculating the nickel oxide band gaps of the films. So we look into so the resistivity measurements from the whole measurements here. We see now a very high resistivity for the nickel oxide and a decrease with temperature, which is very common for metal oxides. And we look into also the arrhenius proportions of the nickel oxide at very low temperatures between 200 and to 300 ones, 250 to 300 temperatures of Kelvin. So there is both the hopping mechanism of the electric charge transfer between the grains, and also we have also a kind of band activated ones depending on the temperatures. So you manipulate the temperature, the conduction parameter at different temperatures of the sensors. So we look into also the mobility of the nickel oxide. So when we see this is an increase with temperature ascended, and then it reaches a plateau where there is a change of the conduction mechanism in this case. Maybe it could be a band gap activated ones, or maybe it is an hopping mechanism at lower temperatures. So the charge carrier transport mechanism attributed to hopping between the colloidal states, causing a relatively low charge carrier mobility, which is here, very low carrier density mobility at low temperatures. This is very important when we are doing with nickel oxide, which is at what temperature we have to look into the mobility or the carrier densities maxima. So having this information, and we will look into the device that this is a kind of a device. We have a different type of, let's say we produced 6 devices. So in each device, we have a Pristine nickel oxide, nanoparticle, gold nanoparticle coated nickel oxide, and we have also copper nanoparticle nickel oxides. So the idea is to see how the nickel oxide is at the Pristine and the decorated could also interact with different gases. So we have a kind of hybrid system. This hybrid device has now commercial sensors and the nickel oxide or different, let's say, functionalities, and to see now how every device interacts now with the different type of sensors. And we optimize now the temperature for the nickel oxide, which is about 150 50, 160 degrees centigrade. And the gases were selected to present now a wide variety of chemical different volatiles in excited phase analysis. So this device were meant to develop now for excited phase analysis. So we look into these carbon dioxide and NO2, water, and also acetone ones. So these are mostly dominant gases in excited phase analysis. So we want to see how these gases are affecting now for each pristine ones nickel doped with gold nanoparticle and copper oxides. So this is the general data we obtained from the different devices. So these are the commercial sensors normally. We look into the sensors what we have locally developed in the nickel oxide ones. So test experiments were with 2 butanol at 95% of relative humidity and 35 degrees centigrade and with 4% of CO2. So the system was maintained at 35 degrees centigrade so that there will not be any kind of let's say humidity retaining on the devices. So we have measured with different concentrations of CO and nitrogen dioxide. We keep these oxides because NO2 is the most oxidizing gas, and we have CO2 is also most reducing gases. So we want to see how these two gases are interacting with the different nickel oxides. So as you can see here, this is the sensor responses for nickel oxide and the ones decorated with gold nanoparticles and copper oxides. So for copper, mostly the pristine nickel oxide gives, let's say, a better response sensitivity than the others. Almost none of this, which is a negative values. So which means CO is very difficult gas. But with nickel oxide, which is a very catalytic surface for carbon monoxide, we have now better sensitivity than the nanoparticle decorated nickel oxides. So which means sometimes nickel, the pristine oxides are much better sensitivity than the nanoparticle decorated ones. And we also see with the NO2 gases, so we have now gold nanoparticle decorated will have the gold nanoparticle will have now better sensitivity than the ones nickel oxides. So I will proceed with the next one. So I will take the slide from the previous presenters. So in most cases, we see in the nanoparticles decorated ones and the grain boundaries ones, but mostly there is a very important parameter that is the porous films. The porous films will produce now more active sites for the oxide or the analyte interactions, analyte absorptions. So we look into the porosity of the materials so that we'll have now more surface interactions. So finally, my conclusion would be we have produced highly and porous nickel oxides with the AGD ones. And we also, the micro study will give a metal nanoporous polycrystalline films with a wide band gap of 4 electron volts. And we also, the whole measurements gives are now a band activation conduction and open activated conductions come into play at lower temperatures. So the gas sensor based on pristine will have now produced now better sensitivity towards CO, and also the gold nanoparticle gives you, let's say, high response towards NO2 gases. So sorry, thank you.
Thank you for your presentation.